Alright, this is section 3.2, Logarithmic Functions, part 2. Again, the essential question for this was, what is a logarithm and how are they used? Alright, so we left off starting with example 6 here. In this example, we want you to graph f of x is equal to 2 to the power of x and g of x is equal to log base 2 of x in the same rectangular system. So what we'll do is we'll start with our 2 to the x. So if I just create some values, so if I start with x and 2 to the x, and we go ahead and pick values, say like -2, -1, 0, 1, and 2, like we did previously, we can quickly calculate these out to be, so when x is -2, we get 1/4, because remember, 2 to the -2 is the equivalent of 1 over 2 squared. So when x is -1, we get 1/2. When 2 to the 0 power is 1, 2 to the first power is 2, and 2 to the second power is 4. So I'll quickly graph these. Alright, so here's the graph for f of x. So let me write that in red. So that's f of x in red. Okay, and now we want to do g of x being log base 2 of x. So quickly let me do this. Okay, but really quickly what I want to point out is that if we take log base 2 of x and make it equal to y, I can rewrite this in the form of 2 to the y power is going to be equal to x. So here, for all of these, I'm actually going to pick the y value first and see what 2 to that y value and get my x. So this is going to be right here. We're going to pick a y value, and then this is going to be 2 to the y, because 2 to the y was x. And I'm going to pick the same exact values. So -2, -1, 0, 1, and 2. So 2 to the -2, again, is 1/4. Then it's 1/2, 1, 2, and 4. Okay, so now I'm going to go ahead and sketch all those. So here what you see in blue is g of x plotted based upon all these blue values we came over to the left. And what I'd like you to remember way back from the beginning of the school year is inverse functions are symmetric along the line y equals x. So if you were to fold this graph over at this dotted line, both these lines would lay on top of each other, meaning this line right here, if we fold it over to this way, it would lay right on top of that. Okay, and we can remember that because they're inverses of each other. So here's just another graphical representation of f of x being any type of exponential function, and then the inverse being the log function. Again, we have our line y equals x, and they are symmetric along that line. And it works the same way if we have a decreasing exponential function. If we were to flip it, okay, it would look like that. So what I kind of would like to clarify here is for our blue functions, or our exponentials, okay, the domain is all real numbers, so from -infinity to +infinity. The range is from 0 to infinity, meaning it never drops below the x-axis. For logarithmics, the domain, it actually switches, and you can see that. So the domain goes from 0 to infinity, and remember those are all the possible x values, and the range is from -infinity to +infinity. Similarly, when we did this with exponential functions, I flashed this up here to show you how all the shifting plays out when we're sketching any types of translations. What I really want you to pay attention to here is the vertical translation, the horizontal translation, the reflections. It's all the same. So vertical changes. All of these functions change vertically when this c value is outside the parentheses. It's a horizontal translation when it's inside. It's a reflection when there's a negative, and then stretching and shrinking. So it's vertical stretching and shrinking when there's a c value in front, horizontal when the c value is on the inside. So this isn't really anything new. So what I'd like to do now is let's find the domain of log base 4 x plus 3. And this type is very simple, because all we have to do here is look at this graph. So I'm looking at the graph. It starts here. So here's my horizontal or my vertical asymptote, and it starts here and then goes off forever in this direction. Okay, so for this type of problem, the domain is from -3 to infinity. Okay, but let's say we didn't have the graph. So if we didn't have this graph, if I just have f of x is equal to log base 4 of x plus 3, we take the inside and set equal to 0. Okay, so x plus 3 is equal to 0. Solve for x, so if I just move the positive 3 over, x equals -3, that gives me my vertical asymptote. So that tells me it's going to be everything right of that value. Alright, so here is just a very simple model. So this model right here is the percentage of the adult height attained by a boy who is X number of years old. So for example, if a child is a newborn, or say 0, we get f of 0 is equal to 29 plus 48.8 log 1. And if we remember from the other day, log 1 is just equal to 0. So this whole term goes away. So f of 0 is equal to 29, or when a newborn is born, they're at 29% of adult height. So here it's asking, what is the percentage of adult height by age 8? So f of 8 is 29 plus 48.8 log of 9. What I'd like to really point out here is when you don't see a number here, so right here they didn't give us a number as the base. So when it's blank, that means 10. Okay, so go ahead and plug that into your calculator with base 10 and figure out what f of 8 is. And go ahead and pause this, and then when you're done, we'll go on to the next slide. Alright, so here are some important properties to know. So log 1 of any base is 0. And then over here, this is just log 1, because here for all of these ones, let me get my pen, these are all base 10. Okay, so here log base b of b is 1, log 10 is 1. So it's really helpful to know what all these are. Alright, so now we're going to look at natural logarithms. And I touched on this a little bit before. Here in previous problems, we've had log base e. Anytime you see log base e, we always write it as the natural log. And it's ln because the French got to it first, and they like to switch around words on us. So that's why it's the ln of x. And we don't say ln, or we typically always say the ln of x. Okay, so we want to find the domains of the natural logarithmic functions, and it's absolutely no different than doing the domains of the regular log functions. So here, for part A, I want to take this inside and set it equal to 0. So 3 minus x is going to be equal to 0. And then I'm going to solve this to get x is equal to 3. This is my vertical asymptote. Okay, and typically what everybody goes ahead and says is the domain is, okay, that's great, it's from 3 to infinity. And if you do that, I'm sorry, but you're wrong. So what we have to look at here is inside this parentheses right here, all right, it always has to be a positive value. So if I use this 3 to infinity, let's say 4 is a part of this, if I plug in 4 here, I get a negative number. So what that tells me is 3 is the absolute largest it can be. So really the domain is from negative infinity to 3. Okay. Okay. Now for the second one, it's slightly different. So what we have here is that we have the ln of x minus 3 squared. And what I want to keep in mind here is, let me rewrite it. Okay, so this can be rewritten as the ln of x minus 3 squared. So just this part right here is being squared. So when I set that equal to 0 and solve, we know that here x cannot be, or x is equal to positive 3. So again, that's my vertical asymptote. Now, if I plug in values that are less than 3 and greater than 3, so for example, let's plug in 4, I get a positive number. So 4 minus 3 is 1, square that, I get 1, so that's fine. Now let's use like negative 10. If I plug in negative 10 here, minus 3, oh look, that's negative 13. If I square that now, that's positive 169. So whatever I use, I'm going to get a positive value. The only thing that's not allowed to be here is 0, so 3 minus 3 is 0. So the domain for the second one is going to be negative infinity to 3 and 3 to positive infinity. Or if you wish, x is a member of all real numbers such that x is not equal to 3. All right, either one of those notations is sufficient. Okay, so for checkpoint 10, what I'd like you to do is do part A and B, find the domains of each of these two functions. So try to find it, then I'd like you to graph it and confirm what you have, and then unpause it and see what I have. So go ahead and pause now, please. Alright, so just like the last problem we did, if I were to substitute, so we found the asymptote to be x equals 4, and that's just by setting the inside equal to 0. So if I pick a value, and let's go ahead and pick 5, if I pick 5, that's going to give me a negative number here, which means that isn't valid. But if I pick 3, 4 minus 3 is 1, so that's valid, so that tells me that my domain is from negative infinity to 4. For the second one, well, if x is 0, that's the obvious one. But remember, because of this square, that means the value of x squared is always a positive number, no matter if it's positive or negative. So the domain is going to be all numbers except for 0. This slide here is identical to a slide we saw a couple back. I think it was like slide 8. The general properties here, and then they gave us the natural logarithms. Note that if these bases were all e, they would be this right here. This is absolutely important to remember. So the ln of 1 is 0, the ln of e is 1, the ln of e to the x is x, and e to the ln of x is just equal to x. It's very important to remember those. Alright, so last time we had you do page 410. 3 through 13 odd, and 21 through 31 odd. So this was part 1's assignment. This is part 2's. Okay. Please have both of these done and turned in by Friday. Thank you.